Whether or not future data fully validates timescape cosmology, cosmic voids remain an important focus for modern astronomy. Understanding matter distribution, how galaxies and filaments connect, and how cosmic web structures change with time can sharpen our models. The next generation of surveys and telescopes, each offering wider coverage and better resolution, may reveal the detailed relationship between voids, clusters, and the passage of cosmic time. In a universe shaped by random quantum fluctuations and chaotic matter distribution, we might expect galaxies to form spinning in random directions. Yet several observations of thousands of galaxies suggest there could be a pattern where more galaxies rotate in a particular orientation. This has startled astronomers, as it hints at a large-scale order that isn't easily explained by standard pictures of the Big Bang. The concept of a preferred direction or axis in the cosmos is not entirely new. Another challenge involves the possibility that time itself doesn't flow at the same rate everywhere. Some new theories, like timescape cosmology, suggest that variation in the flow of time across regions with different gravitational potentials could mimic the effects of dark energy. If time runs faster in vast empty regions of the universe, then clocks in those areas would measure different rates of expansion, making it look like the universe is accelerating. This reasoning doesn't mean dark energy doesn't exist, but it does question whether we fully understand what signals we're detecting in our observations. Researchers are also probing whether dark energy could be tied to quantum fluctuations of empty space, or if it could relate to other unknown fields, like quintessence, that vary over time. These speculations open up vast possibilities that have yet to be ruled out by observations. Because JWST can peer deeper into the early epochs of the universe, it offers a crucial test of how galaxies evolve and how expansion behaves at different cosmic times. Even the measurements of how structures like galaxy clusters form can test dark energy. If dark energy has remained constant, clusters form at a specific rate. If dark energy changes, it would have different effects on the collapse of cosmic matter into clusters. Comparing these predictions to actual counts of galaxy clusters and their distributions at different points in time is a way to check the consistency of the theory. For now, dark energy stands as one of our universe's biggest mysteries. It's possible that we'll need to tinker with Einstein's equations or introduce brand new physics to explain the data we're getting better at gathering. The deeper we look, the stranger the universe can appear. As new data arrives from JWST and future telescopes, our understanding of dark energy, whether it's truly uniform or changing, will likely keep evolving. Timescape cosmology is a fresh concept that seems to solve some thorny problems in our standard outlook. Instead of introducing a mysterious form of energy, this approach suggests that the observation of accelerating expansion might be an illusion caused by the way clocks run differently in regions with varying density of matter. In this viewpoint, galaxies are not isolating themselves from each other faster and faster due to an invisible force, but rather, time itself could be playing tricks on us. For instance, if time runs at a different pace within galaxy clusters than in cosmic voids, observational data can appear as though the universe is expanding unevenly. Large underdense areas, voids, might be aging faster compared to denser clusters, meaning that from our vantage point, objects near or across these voids would look like they're zipping away more quickly. This idea challenges the usual assumption that there is a single universal age that applies everywhere. Traditionally, when cosmologists speak of a 13.8 billion-year-old universe, they tend to treat time as flowing at the same rate for all corners of space. Timescape cosmology says that assumption might be oversimplified. Over billions of years, even a small difference in how time flows can add up. Proponents of this model believe it can address the Hubble tension and provide new ways to interpret cosmic data without resorting to a static uniform dark energy term. Instead, the accelerating expansion emerges from the geometry of space-time shaped by an uneven distribution of matter. To test these ideas, researchers compare them to large-scale surveys and observations, checking whether these predictions better match what telescopes recall. So far, some tests suggest timescape cosmology can match observations about as well, or in some cases slightly better, than the conventional model. Though intriguing, timescape cosmology is still considered a minority view in astrophysics. It requires careful mathematical treatments that can be more complex than the standard model. Many scientists remain cautious, noting that we have to be sure we're not missing other more straightforward explanations. For instance, could dark energy be a dynamic phenomenon that changes over cosmic time? Could new physics, like modifications of Einstein's theory of gravity, replicate these observational patterns? The point is not that Einstein's relativity is wrong. Rather, the idea is that we're applying our cosmic averages in a way that might be too simplistic. We assume the universe looks roughly the same in all directions, isotropy, and that it's homogeneous on large scales. Timescape cosmology says that even if the matter distribution looks roughly even when viewed from far away, small differences in density can lead to different clocks for different cosmic regions. Continuing studies will help determine if this approach can survive in the face of growing JWST data. If we see that early galaxies appear unexpectedly mature, or certain groups of galaxies show signs of cosmic times that differ from what standard dark energy models predict, that would be a significant hint. Timescape cosmology is thus part of a growing set of alternatives that may revise our thinking about cosmic expansion and the underlying reasons behind it. The James Webb Space Telescope has delivered striking images and data from early cosmic time, sparking a wave of curiosity and debate. Positioned far beyond Earth's atmosphere, JWST can capture infrared light emitted by ancient galaxies that formed over 13 billion years ago. Its powerful instruments reveal details that were previously hidden. While astronomers expected to see small, clumpy galaxies in the young universe, JWST found many that were surprisingly big and already well-structured. One particularly famous example is the galaxy nicknamed the Big Wheel, which showed up in JWST's observations as an enormous disk-like system. You'd think, according to standard models, that it would take much longer for galaxies to reach that level of development. The presence of such a large, rotating structure in the universe's infancy suggests that either star formation and galactic organization happened at a rate far higher than we anticipated, or that our timelines are off. These surprising finds have big implications because cosmologists use the distribution and properties of early galaxies to tune parameters in their models. For instance, how quickly galaxies cluster or how massive they become by a certain point in cosmic history ties into the presence of dark matter, the strength of dark energy, and the specifics of cosmic inflation. If galaxies started out bigger and more mature, then either the universe had more time to form them, hinting that it might be older in some sense, or the process of galaxy building is more efficient than we realized. Another puzzle emerges when we consider the heavier elements found in some early galaxies. Elements beyond hydrogen and helium have to form through nuclear-directed reactions inside stars. These stars then explode in supernovae, spreading these heavier elements. If we spot surprising amounts of these elements in early galaxies, that indicates multiple generations of stars were born and died quite fast. This raises questions about how star formation proceeded so swiftly in the young cosmos. Another aspect that occasionally surfaces is the possibility that we've misread distances. If a galaxy is not actually as far away as we thought, it might merely appear to be an early galaxy due to a confused signal. This is why astronomers use multiple lines of data, like specific emission lines of elements, to confirm redshift values. While there can be some mistakes in individual distance measurements, there are just too many examples piling up for them all to be flukes. All this excitement about early galaxies plays directly into the debate about whether the Big Bang Theory, cosmic inflation, and standard expansions are the whole story. Most researchers don't think the Big Bang model is wholly incorrect. There's too much evidence, like the cosmic microwave background, in its favor. But these puzzling galaxies might indicate we need to adjust or expand the model. That could involve reviewing how structure forms in the presence of dark matter and dark energy, or even exploring entirely different frameworks, like timescape cosmology or modifications of general relativity. One of the more captivating ideas to come out of modern cosmology is that vast empty regions of space, called cosmic voids, are not just boring stretches with little matter. They might play a key role in shaping the universe's behavior on a large scale. In standard models, voids are regions left behind when matter clumps together to form galaxies and clusters. They continue to enlarge as structures grow, but they don't usually get center stage in discussions about cosmic evolution. Enter the concept that time might flow differently depending on the local gravitational potential. According to timescape cosmology, if time flows faster in voids than over billions of years, these emptier areas might be older compared to denser regions. This difference could create the impression of an accelerating universe if someone located in a denser region looks out across cosmic distances. Voids themselves are not uniform. They can contain small galaxies, wispy filaments of gas, and, of course, dark matter, but compared to clusters of galaxies, they're underdense. If time is passing more quickly there, any process that depends on time, like the expansion of space, might appear more advanced within these voids. The challenge is confirming such an effect with observations. Researchers compare the distribution of galaxies and how light moves through these regions. They also look at gravitational lensing data, in which a massive object bends light from a source behind it. If time and space behave in unusual ways, the lensing signals might hold clues. Some recent observational surveys have tried to carefully map cosmic voids to see how they expand. The results have been intriguing, but not yet definitive. The branching out of these ideas stems in part from the puzzling data coming from JWST and other observatories. If galaxy evolution seems faster in certain areas, or if cosmic expansion appears to be inconsistent, could it be that regions of the universe are on different timelines? While this might sound almost like science fiction, relativity itself teaches us that time is not absolute. Gravitational time dilation has been observed near massive bodies like Earth and the Sun. On cosmic scales, the effect might be small, but accumulates over billions of years, causing measurable differences. Skeptics argue that a variable flow of time might conflict with simpler explanations. Maybe the rate of star formation or the mass of the earliest stars was just greater than we once assumed. Maybe dark energy changes in strength over epochs in a way that accounts for these discrepancies. The supporters of the voids and time differences model insist that we should keep an open mind, as it potentially solves more than one puzzle at once without needing an unobserved substance like dark energy. Whether or not future data fully validates timescape cosmology, cosmic voids remain an important focus for modern astronomy. Understanding matter distribution, how galaxies and filaments connect, and how cosmic web structures change with time can sharpen our models. The next generation of surveys and telescopes, each offering wider coverage and better resolution, may reveal the detailed relationship between voids, clusters, and the passage of cosmic time. In a universe shaped by random quantum fluctuations and chaotic matter distribution, we might expect galaxies to form spinning in random directions. Yet several observations of thousands of galaxies suggest there could be a pattern where more galaxies rotate in a particular orientation. This has startled astronomers, as it hints at a large-scale order that isn't easily explained by standard pictures of the Big Bang. The concept of a preferred direction or axis in the cosmos is not entirely new. Some earlier studies of the cosmic microwave background pointed out anomalies like the so-called axis of evil, where tiny temperature fluctuations in different sky directions appeared to have a strange alignment. Experts debated whether these anomalies were measurement artifacts or if they pointed to a new phenomenon. Now, the idea that galaxy spins might show a directional preference adds more data to that debate. If such a directional bias is confirmed on large scales, it could mean a couple of things. Number one, an early spin, perhaps the entire universe inherited some initial rotation. This idea taps into questions about whether the Big Bang itself was rotational in any sense. Standard theory generally doesn't include a net spin, assuming an isotropic and homogeneous expansion, but a small initial rotation could, in principle, seed patterns that remain visible in galaxy spins. Number two, cosmic scale fields. Some exotic models suggest that early magnetic fields or other large-scale phenomena might have oriented galaxy spins. Such large-scale fields are not well understood. It's possible they formed under certain conditions soon after the Big Bang, influencing how matter condensed into halos of dark matter and later galaxies. Either scenario challenges the usual randomness assumption embedded in standard cosmology. Over billions of years, collisions and gravitational interactions might shuffle galaxy spins to some degree, but if a strong initial orientation was present, a statistical signal could remain in the data. At the moment, these signals are subtle enough that astronomers are gathering more evidence. The possibility that galaxies line up or rotate in a particular pattern also relates to the idea that the universe might be more structured than thought. It ties back to questions about large-scale flows, cosmic voids, and materials bridging clusters of galaxies. If these patterns aren't random, they might link to the presence of filaments in the cosmic web that guide how galaxies form and evolve. Understanding that structure can help us refine models of the early universe, including whether inflation or other processes introduce distinct directional features. Whatever the final explanation, the very suggestion that our cosmos has a preferred spin direction shakes up a key assumption about isotropy, the idea that all directions in space are equivalent. Probing these large-scale rotational patterns is yet another way that new data is prodding us to reconsider or expand upon the standard cosmological narrative. Future telescopes, combined with improved galaxy catalogs and enhanced ways of measuring rotational directions, should shed more light on whether these alignments are real and, if so, what they might mean for how we model the origin and evolution of cosmic structures. Before dark matter and dark energy dominated discussions, one of the key features of modern cosmology was cosmic inflation. This is the idea that in the first tiny fraction of a second after the Big Bang, the universe grew exponentially fast, smoothing out inhomogeneities and explaining why it appears so uniform on large scales. Inflation was introduced in the early 1980s to make sense of why the cosmic microwave background looks nearly the same in all directions, among other puzzles. Most inflationary models assume a scalar field, sometimes called the inflaton, that drove this exponential expansion. When inflation ended, the energy of that field presumably converted into particles, starting the hot Big Bang phase. This framework helps solve problems like the horizon problem, why distant regions of the universe have similar properties, and the flatness problem, why the universe's geometry is so close to flat. Over the decades, cosmologists have refined inflation to better match data from probes like the WMAP and Planck satellites, which measured the cosmic microwave background with high precision. However, inflation is not without its controversies. Some variants predict gravitational waves from the early universe that remain undetected at the levels expected. Also, theories of eternal inflation suggest that inflation might never fully end, leading to a multiverse scenario. Critics argue that inflation can be a bit too flexible. When new data arises, theorists can tweak inflationary models to fit. The JWST revelations about early galaxies, if they suggest a different timeline for structure formation, might indirectly affect how we view inflation. Inflation doesn't directly dictate how fast galaxies appear, but it sets the stage for initial density fluctuations. If galaxies are forming faster or bigger than expected, that might suggest these initial fluctuations were stronger or had different characteristics than standard inflationary models propose. Alternatively, something else, like variations in how time flows or different forms of dark energy, could overshadow inflation in explaining early structure. Moreover, some scientists wonder whether inflation is truly the only explanation for the uniformity of the cosmic microwave background. If the concept of time variation across cosmic voids becomes mainstream, could it also explain the observed patterns without standard inflation? You'd need a consistent framework that accounts for the near isotropy of the cosmic microwave background and the distribution of galaxies. Still, the majority of cosmologists remain supportive of inflation, as it elegantly solves multiple cosmic riddles in one go. In the future, better measurements of the cosmic microwave background polarization and new gravitational wave detectors might confirm or challenge details of inflation. Until then, inflation stands as a core pillar of the Big Bang narrative, albeit one that might need refining in light of ongoing surprising discoveries about early galaxies. We often mention the Hubble tension as something that emerges from two main methods of measuring the expansion rate. One uses the cosmic microwave background combined with the standard model, resulting in a lower predicted expansion rate, and the other focuses on local measurements of supernova distances and galaxy motion, resulting in a higher expansion rate. These two numbers don't match, and the discrepancy is larger than the margin of error would allow. This open question highlights possible gaps in our cosmological framework. One easy route is to suggest new forms of energy or matter in the early universe that shift the expansion rate. Another is that our local environment is unusual. Maybe we live in a cosmic void, which would affect distance measurements of other galaxies. Timescape cosmology also addresses this by tweaking how we see cosmic time and expansion. If we add JWST's data showing giant mature galaxies forming earlier than standard timelines predict, it hints that we might need an overhaul of how the early universe was structured. Could the real story be that the Big Bang is correct in broad strokes? There was indeed a hot, dense beginning, but the details about expansion rates and matter distributions require changes? Or is it more radical, suggesting we might have to let go of the Big Bang model altogether? Some astrophysicists caution it's too soon to throw out the Big Bang. The cosmic microwave background, abundance of light elements like helium and lithium, and large-scale structure patterns line up strongly with the theory of a hot, dense origin. However, these challenging observations underscore that the Big Bang theory is not unchangeable dogma. Science is about continuous testing, and the tension between different data sets is a prime example of where progress can be made. It's worth noting that the Big Bang itself is not opposed by these observations. Rather, the synergy of inflation, dark energy, and the exact matter distribution is where cracks appear. The phrase Big Bang can be broad, encompassing many aspects of modern cosmology, from the initial singularity to the expansion history and the creation of light elements. Sometimes, when new data doesn't align with the simplest version of the model, we add more patches like inflation, dark energy, or dark matter. But if it becomes too patchwork, we might suspect a deeper conceptual solution, like a major shift in how we view time or gravity. Given the Hubble tension and the puzzling early galaxies, we may be looking at something akin to the shift from Newtonian physics to Einsteinian physics, a step toward a deeper theory that keeps some older insights while expanding on them in ways that solve the new problems. Whether timescape cosmology, black hole birth theories, or other radical ideas will take hold remains to be seen, but it's clear that something fascinating is happening with our cosmic measurements, inviting a fresh wave of creativity and analysis in cosmology.